go ahead and move on to 11.3 and publish it. 11.3. We're going to do what's called the integral test. Okay, so recap. What have we done so far? We have determined how to do sequences. Okay, and when it comes to sequences, you can, you can either find the first term, so you might have to figure out what the connection between the terms are. And then if I have a sequence, I take the limit of that sequence and see if it gives me a number. Tells the version backward. Okay, that's all. 11.2, right? The big ideas, right? We started off talking about just partial sums, right? What a series is, kind of just adding all of these terms together into one big infinite sum, see if it goes anywhere. And we use partial sums to kind of get a couple of examples. The first one was the geometric series. Well, we just some random ones. So the geometric series where we had a over 1 minus r, right, as the sum, and then the r is between -1 and 1, it converges. And then we also have things like the telescopic series, where we can find the sum and see if it converges or diverges. And then we had a big trump card as well, which is the test for divergence, where you have if the limit doesn't go to 0, then you know it just diverges automatically. Okay, so those are going to be things to kind of store up in your mind bank to hold on to. Okay, now we're going to keep adding to that, and each section from here we're just going to add on another test for convergence to divergence. Okay, so we have a few. We're going to do this first one is the integral test. So to demonstrate this one, let's think through a picture. So let's say I have a function 1 over n squared. Okay. Sorry, 1 over x squared in this case. That is going to look like, at least in this portion of the graph, that's all I really care about for now. My graph is going to look something like this. Now, we talked about last time that we can do fn in here. So let's see, instead of looking at this function as it is, let's look at that's kind of its companion essentially. It's sequential term, the term for the series. We're going to write it as 1 over n squared. Now, if I wanted to find the area underneath this thing, it would be easy. We've done that. And so I would go from 1 point, which I'll start at 1 here. And then I would just find the area that goes up this thing. Okay. Now, what if I want to figure out if this thing converges or diverges? At least the series. Fun fact, this does actually converge. I might tell you about it later. It's not a series. But if I want to figure out if that converges, right? Here's the idea, right? Remember when we were doing Riemann sums before, right? To find integrals, right? We would use rectangles and we'd say, okay, do I use left points or do I use right points, right? If I were to take this graph, try to break it up into rectangles and use left endpoints, right? I would get, maybe I'll write 2, 3, 4. I would get this, right? So if I broke it up into rectangles rather than just getting the exact area, right? I would have this little bit above it, and this little section that I want to find right. That I would have to like consider whenever I'm finding the area, but that would be my approximation using 4 rectangles, okay? We also had the option to do right endpoints, right? Which would put me here, 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 and here. Okay. Now, where am I going? Where am I going? Well, if I want to think about what the sum looks like in terms of if I want to see what this looks like kind of graphically. These boxes are what do that for me, right? Because I'm gonna have, right, what's the length of each of these boxes? 1, right? And then my height, right? And we'll do the let's see. We'll do the I want to do the total. What is the height of each blue box in this case, right? So again, they hit their right endpoints hit their left endpoints at the edge of the curve, right? So what is the length of that curve, right? It's f of x, right? It's 1 over x squared, right? Now notice the numbers we're putting in are just our natural numbers, right? So in each case, this is 1 over n squared, right? Right, or it's 1 over x squared in general, but for now we're looking at these boxes, right? So we'll just say 1 over n squared for each term. To find the area of each rectangle, I just take 1 and I multiply by 1 over n squared, right? And then, if I just want to take all of the boxes, right, just keep going until the end, right, and add them up, so I have 1 over 1 squared, plus 1 over 2 squared, plus 1 over 3 squared, plus 1 over 4 squared, plus 1 over 5 squared. That would be the sum. Okay. Now, here's the question, right? I want to take that to infinity, right? Have I done this sort of problem before? Yes, we have. What do we call this? Called an improper integral. Okay. If I do this improper integral, right, I can work this out and I can see if it gives me a value or not, right? Now, in some cases, right, that may not converge, right? So the example, if it was like 1 over x, right, that wouldn't work, right? So let's think about our picture, right? Notice, so tell me this right now. Is this integral or this series going to be bigger? Which is bigger between the two? Not the integral, actually. It's this, right? It's going to be the series because notice all the extra blue space on the boxes, right? Okay. So here's the question. If this integral diverges, which this one doesn't, but let's just say it did, right? And this sum is bigger than that integral, what do you think is going to happen? It's going to diverge. Again, that's the hypothetical case if this one diverges. I know it doesn't in this case. We'll find its exact. We'll be able to compare it, but we can see that clearly from the picture, right? Okay. Similarly, and this one's a little, it may take a little bit more here to think about, but notice this, so the green boxes that I drew, right? Those can also extend, right? This box has the same height as this box, correct? And this box the same height as this one, and this one the same height as this one. So, and maybe I'll write the sum of the green boxes is equal to the sum of the blue boxes, right? Minus just the first big one, right? Because everything else has a match as we go down, right? So all we're doing is taking off this first one. what is the area of this first rectangle, right? It's 1 times whatever n is, which is just 1 in that case. What's 1 times 1? So it's just the sum minus 1, okay? So, the point I'm getting to here is that so the sum of so they're basically off by 1, right? So if this one converges, the blue one, then this green one definitely converges as well, right? Because they're just off by 1 or maybe off by some value, right? So what that means, right, again, if the blue one's converging, then the green one is, and vice versa. The green one is and the blue one is, you just add 1 to it. So, now let's think about this sum in comparison to the green boxes. If this integral converges, is the sum of all those green boxes going to converge or diverge? What do we think, right? Is the sum of the green boxes going to be bigger or smaller than the integral? Smaller, right? Because we took out all of this space. We subtracted that space from the integral, right? So if this converges, then all those green boxes converge, right? And since all the green boxes converge, and the blue boxes are only off by like a bit, then that also means this converges. Okay. All in all, what does this mean? What did we just do? What are we trying to say? We're trying to say this. If I'm given the sum as n goes from 0, I would go to 1. I mean, it doesn't matter again, it goes to 0. N equals 1 to infinity of an. And I want to figure out this converges or diverges. If now, let me see. So let's say an equals some f of n, right? So an is just some function we plug into it, right? Like again, here in the 1/n squared case, it'd be f of n, be f 1/n squared, right? So define if this converges or diverges if the integral from 1 to infinity of f of x dx converges, then the sum from n equals 1 to infinity of an, which is f of n, also converges. If the integral from 1 to infinity or 0, it just depends on what the lower bound is, it doesn't matter, of f of x dx diverges, then the sum from n equals 1 to infinity of an diverges. Okay. We're going to do some examples, it's going to make sense. Okay, but all to say, right? Let's take the thing inside the sum and integrate it instead. If the integral converges, then the sum converges. And if the integral diverges, then the sum diverges. It's going to be as simple as that. Okay. Any questions for me before we hop into this here? Oh, okay, cool. So let's start with that, and maybe actually let's just go ahead, instead of just 1/n, we're going to do 1/n. Actually, let's do 1. Okay, so we're going to find if this integral converges or diverges. I already told you it diverges, but I just want to prove it to you. Okay, so what I'm gonna do is I'm going to take the integral of this thing from 1 to infinity. Now, what function do I use here? Right? Basically what I'm saying there is that everywhere where there's an n, I put an x instead. So what's my function gonna be? 1 over x. Okay, can I integrate this? Yes. What do I need to do first though? Integrate. Okay, now what's the integral gonna be? Good. What's the integral of 1 over x? Good. 1 t. So limit as t approaches infinity, the natural log of t minus the natural log of 1. But what's the natural log of 1? 0. Okay. So we're just left with natural log of t. Does that converge or diverge? How happens if I put infinity in there? Gonna converge or diverge? It's going to diverge, right? It's just infinity. So this is a divergent integral. So what does that tell us about my series? It's also divergent. That's it. Questions for me? No. Okay. So, we can do the same thing with 1 over n squared, which that one actually does converge. We actually worked with that integral a few times. That would be the answer comes out to be 1 for the integral. The sum is not necessarily 1. Okay, I hope that makes sense, right? Again, coming back to our box talk with the with these blue boxes here, right? This is a bit bigger than the integral, right? So because of that, this is gonna be a bit bigger of a number than the integral is gonna be. Still, we can use it to say if it converges or diverges, but don't take the value of this integral and say it's the value of the sum, because that's not true. And I'll prove it to you right here. This is equal to 1. So, any guesses on what 1 over n squared is supposed to be? Just take a wild guess. Anything, honestly. Just whatever. No. It's pi squared over 6. So you probably would not have ever thought of that. But it's true. The sum of 1 over n squared ends up being pi squared over 6. I feel like I've played around before. This gets into discussion of things like it's called Riemann-Stieltjes function, and you get like natural response and all sorts of fun stuff. Anyway, that's not right for now. We're just going to do integral tests to see if it's converge or diverge. Okay. Again, any questions for me? This is all you're doing in this section. All right, you're just doing a whole bunch of integrals. So to see if it converges or diverges. Okay. Let's do some more examples here. Let's do. Yeah, we'll do number 8. So we just want to find if this thing converges or diverges. The sum in this case is going to be the sum from n equals 1 to infinity of n squared e to the negative n cubed. Okay, and it says to determine convergence or divergence using the integral test. So, what's my first step? Yeah, we're gonna have the integral of, and then we'll just, whatever the numbers are here, you plug in for the numbers here. Okay, and then we just replace n with x. Okay, so we want to look at this integral and see if it converges or diverges. Okay, if we want to evaluate this integral, what's my first step? Non-integration moving parts. That would actually make the problem a lot harder. We would want to use substitution, but even before that, right? This is an improper integral, so yeah, so we have to rewrite it as the limit as t approaches infinity of the integral from 1 to t of x squared e to the negative x. Now, yes, absolutely, we are going to use u sub on this. Okay, any guesses on what u is supposed to be? X cubed or negative x cubed, doesn't matter. I'll use negative x cubed. Why not? We'll do like u be negative x cubed, du be. So what's the derivative of negative x cubed? X. So we have the x squared, so I'll move that -3 over there. Okay. Now, u is negative x cubed, right? So I'm going to want to change my mouse as well with that. So I want to get the limit as t goes to infinity of the integral. If I take 1 and I plug it in here, what do we do? -1 cubed. -1. And if I take t and put it in there, what do I do? Negative t cubed. I put t into the negative x cubed, right? I'm putting t. Okay. So that's our balance. And then we're gonna have e, and then we'll have the -1/3 out here. And we'll have e to the u du. Okay. What's the integral of e to the u du? Integral of e to the u du. So it's e to the u, right? The integral of e to the u is just e to the u. And then we're going to evaluate this from -1 to -2 cubed. And honestly, if you don't want to get the value, you don't have to. We just need to see if the limit's going to actually go somewhere, right? So I want to get the limit t approaches infinity of -1/3 e to the -2 cubed plus 1/3 e to the -1. Okay. Is this limit going to converge or diverge? What do we think? All right, this term doesn't mean it's just a number. So if I put infinity in here, is that going to converge or diverge? It's going to converge. It's negative t cubed, so it's negative in like infinity, right? So I actually bring that to the denominator. So I get -1/3 e to the t cubed. So take that to infinity. That whole thing goes. So this integral converges or diverges. You can find that it's like 1/3. So this converges. So what does that mean about the series? It also converges. Okay. So what is this section? It's 7.8 again, except there's an extra step. That's all. Okay. Good. Yeah. Otherwise, in the it does talk about the root and zeta function. I'm not going to talk about it, but it is the problem. It's number 33. there's other, basically you're just doing that the whole time, see if you can find the integral. There's like a couple problems that ask like why you can't use integral tests. It's just because you can't do the integral. Like one of them's cosine squared integral 1 plus n squared. Good luck trying to do that. Like hit that to integrate that. And then there's some where you might be given like a general value of, like I wrote earlier with like you have some p-value, and then the questions are going to be if that converges to divergent. Okay, now close this off. I'm going to give you the easiest test possible. Okay, that comes from knowing the integral test and doing it. Okay, which is called the p-series test, and this is a p-series right here. It has to look like 1 over n to the p power. Okay, if there's a number on it, that's fine. You can bring it out or whatever, but it needs to have n to the p on the bottom. Okay, if p is greater than 1, it converges. If p is less than or equal to 1, diverges. Again, let me reiterate, as long as you're greater than 1, so you can be 2, 3, 4, 5, you can even be 1.1 or 1.01, whatever it is, it's convergent. Okay, so I could have known 1 over n and 1 over n squared were convergent right off the bat, knowing this, right? Of course, it requires doing the integral test to get to that point, but this is kind of shorthand. And then if it's less than or equal to 1, obviously the harmonic series, we talked about divergence already, and then actually, so right there. But if it's less than 1, if it's 1/2, 1/4, even if it's 0, -1, -2, divergent. Okay. So. Not quite, but come back tomorrow. We'll talk about how we can still use this for some way. So we'll do comparison. So, thank you all for today. Yeah, you too. Thank you.